Hello, and welcome to this presentation on vectors, specifically looking at vector products. This is part 2 of the presentation, so it's assumed you've already reviewed part 1, which looks at the theory behind the vector products and how we solve them using determinants. This part 2 will now take that theory and apply it to some worked examples and exercises and leave you with some questions to attempt. This slide is a recap of that shown in part 1 of the presentation, just included here for convenience. It outlines the vector product, A cross B, in determinant format, and also how we find the magnitude of a vector product using Pythagoras' theorem. We'll be using this information now to underpin the work we're going to do for the examples and exercises that follow, where we're applying this theory to solve particular problems. So let's look at an example now of applying our vector product process. In example 1, we're given vectors A, which is I plus 4j minus 2k, and vector B is 2i minus j plus 3k. We're firstly asked to find A cross B, and secondly to find the magnitude of A cross B. So let's look at part 1 first of all. So we can write the vector product A cross B in determinant form. We know from our previous slide the I, J, K column can be then filled in with the A1, A2, A3 for the vector A and the B1, B2, B3 coefficients for the vector B. So we're now going to solve our determinant using the process outlined on the previous slide. So in this particular example we've got A cross B, where the A1I is 1, the A2j is 4, and the A3k is minus 2. We get that from the question. And then for vector B, the B1i is 2, the B2j is minus 1, and the B3k is plus 3. Again, we get that from the information in the question. Example 1 continued. I just repeated the A cross B determinant here for convenience. We're now going to solve for individual I, J and K components. So the plus I, our determinant here will be 4 minus 2 minus 1, 3. And we get that by covering up the I column and reading the coefficients. Our next determinant is minus J, and the coefficients are 1, minus 2, 2 and 3. And we get that by covering up the J column and reading the coefficients. And our final determinant is plus K, and we've got coefficients of 1, 4, 2 and minus 1. And we get that by covering up the K column and reading the coefficients. So evaluating the individual determinants, the plus I, we've got 4 times 3, take away minus 1 times minus 2. So be careful of the directed numbers here. There's the 4 times 3 take away, and then the minus 2 times the minus 1 will be a plus 2 there. So we'll end up with 12 take away 2 equals 10 in the I. Just be careful of directed numbers. Very easy to make a mistake with the negative signs. For the minus J determinant, we've got 1 multiplied by 3 take away the minus 2 times 2. So 1 times 3 take away minus 2 times 2. Again, be careful of your directed numbers. That 3 take away minus 4 gives us 7. And finally for the K component plus K, it's 1 times minus 1 take away 4 times 2. So 1 times minus 1 take away 4 times 2 gives us minus 9. So we can now write down the A cross B vector product. That will be plus 10 in the I, minus 7 in the J, notice a negative here we have to carry through, and then plus the minus 9 in the K. Just tidying it up on the next line, that's 10i minus 7j minus 9k. If we want the magnitude, then we use Pythagoras' theorem in 3 directions, so that will be 10 squared plus the 7 squared plus the 9 squared all square rooted. Gives us 15.17. Exercise 1. We're asked to find the vector product A cross B given vectors A and B, and also the vector product B cross A. We're asked then to compare A cross B with B cross A. The answers are given here in the square brackets. I'd encourage you to attempt this exercise before looking at the solutions on the following slides. Exercise 1. So we're asked to find vector product A cross B given vectors A and B, and then also find vector product B cross A. We're going to compare the two once we've done that. So part 1 here is the A cross B vector product. In the question we're given the vector A is 1i minus 1j plus 2k. I'm going to multiply that by the vector B, which is 2i plus 0j plus 1k. So using our standard process for calculating vector products using determinants, in this particular case our A cross B using our I, J, K column headings will be 1 in the I, minus 1 in the J, 2 in the K for vector A, and 2 in the I, 0 in the J, 1 in the K for vector B. Exercise 1 continued. I just repeated the A cross B determinant for convenience. So we're now going to break this down into the ijk component. So the plus I will have the coefficients of minus 1, 2, 0 and 1. And again we get that by covering up the I column here. To get the minus j coefficients, that will be 1, 2, 2 and 1. Again we get that by covering up the j column and reading the coefficients. And finally, to get the plus k determinant, that will be 1, minus 1, 2 and 0, and we get that by covering up the k column and reading the coefficients. Going to now evaluate the 2 by 2 determinant. So the plus I determinant will be minus 1 times 1, take away 2 times 0, so shown here gives us minus 1. For the negative j determinant, that will be 1 times 1, take away 2 times 2, shown here, gives us a value of minus 3. And for the positive k determinant, that will be 1 times 0, take away the minus 1 times 2. That gives us a value of positive 2. So from above, the A cross B vector product will be minus 1i minus a minus 3j, again notice that negative we've got to carry through, plus a 2k. So just tidying that up, A cross B is minus 1i plus 3j plus 2k. Exercise 1 part 2, we're now going to work out the vector product B cross A. So now we've got our B vector 2i minus 0j plus 1k, and that's multiplied by the A vector, which is I minus j plus 2k. So writing the B cross A determinant, we will get 2i 0j 1k for the B vector, and for the A vector it's 1 minus 1 and 2. Exercise 1 part 2 continued. Just repeated our vector product B cross A here for convenience. We're now going to solve for the B cross A vector product in terms of the I, J, K determinants. So for the I determinant, our coefficients are going to be 0, 1, minus 1 and 2, and we get that by covering up the I column and reading the coefficients to the right hand side. To find the minus j determinant, the coefficients are going to be 2, 1, 1 and 2, and we find those by covering up the j column and reading the coefficients to the left and the right. And to find the plus k determinant, the coefficients are 2, 0, 1 and minus 1, and we find those by covering up the k column and looking at the coefficients to the left. So solving for the I determinant, that will be 0 times 2, take away minus 1 times 1, gives us a value of 1. For the minus j determinant, that will be 2 times 2, take away the 1 times 1, gives us 3. And for positive k, that's going to be 2 times minus 1, take away 1 times 0. That gives us minus 2. bringing the terms together, b cross a can be written as 1i minus 3j plus the minus 2k. Don't forget we've carried the negative j through to here, as always. Just rewriting that, I get I minus 3j minus 2k. What we notice is that the b cross a vector product is of the opposite sense to the a cross b vector product we found previously. So as a summary for exercise 1, parts 1 and 2, we can now say that vector product a cross b does not equal to b cross a, but vector product a cross b does equal to minus b cross a, or the magnitude of vector product a cross b is equal to the magnitude of vector product b cross a. Example 2, we're given vector p, q and r in a unit triad notation. Part 1 wants us to find vector p, take away 2 times vector q and then cross with r. And part 2 wants us to find vector p cross with 2r times by 3q. So part 1, we've got vector p, take away 2 times vector q in the bracket, and then that's multiplied by vector r. So the first thing we need to do is to solve the bracket. So vector p from the question is 4i plus j minus 2k, and we take away from that 2 times vector q. Vector q is given as 3i minus 2j plus k, and we're crossing that with the vector r, the I minus 2k. So be careful of the bracket here. We've got to multiply each of the terms by 2, and there's a change of sign, of course. So we get 4i plus j minus 2k, that's vector p, and we're taking away now 6i, 2 times the 3i, we're adding 4j, minus 2 times minus 2 is plus 4, and we're taking away the 2k, the minus 2 times the 1k. Vector r here. So tidying up inside the bracket, bringing our like terms together if you want to think of it that way. So 4i take away 6i gives us minus 2i, plus 1j plus 4j gives us 5j, and then the minus 2k is minus 4k. And that's all multiplied by the vector r. So now we can use determinants to multiply the bracketed term by vector r. So putting that into our determinant form, so p minus 2q all times the vector r on our I, j and k notation, we will get minus 2, 5 in minus 4 for the bracketed term p minus 2q from above, and then for a vector r we get 1, 0 in the j and minus 2 in the k. Example 2, part 1 continued, just repeated the determinant for p minus 2q times r for convenience. So now we're going to form our 3 individual determinants. For plus I, the coefficients are 5, minus 4, 0 and minus 2, and we get that by covering up the I column and reading to the right. For the minus j determinant, the coefficients are minus 2, minus 4, 1 and minus 2, and we get that by covering up the j column and reading the coefficients to the left and the right. And the plus k determinant, the coefficients are minus 2, 5, 1 and 0, and we get that by covering up the k column and reading the coefficients to the left. Now evaluating the determinants, so for the plus I, that becomes 5 times minus 2, take away 0 times minus 4, gives us minus 10. For the minus j determinant, that's minus 2 times minus 2, 1 times minus 4, that gives us plus 8. And for the plus k determinant, that's minus 2 times 0, take away 1 times 5, gives us minus 5. So now p minus 2q all multiplied by r gives us minus 10 in the I, minus 8 in the j, plus minus 5 in the k. Again, be careful of the negative j sign we have to drag through here. Tidying that up, we get p minus 2q multiplied by r is equal to minus 10i, minus 8j, minus 5k. Example 2 continued. I would encourage you to attempt part 2 of example 2. You've got to find vector p crossed with 2r times 3q in the brackets there. A very similar process to undertake as was performed in part 1 of example 2. As a hint now, work out the 2r times 3q vector first of all. So in other words, factor vector r by 2 and then factor vector q by 3 and multiply those terms as a cross product. And then form the cross product of p multiplied by the 2r and crossed with 3q. The answers are given here and the solutions are shown on the following slides, but I'd encourage you to stop the video and attempt part 2 of example 2. So example 2, part 2 solution. We're asked to solve vector p crossed with in brackets 2r multiplied by the 3q. We're given in the question that vector p is 4i plus j minus 2k, and we're going to cross this with the bracketed term there, 2 times r, so 2, and vector r was given as I take away 2k, and we're multiplying that by 3 times vector q, which was 3i minus 2j plus k. On the next line I've just repeated the vector p and I've expanded the brackets here, so I get 2 times I is 2i, 2 times the minus 2k is minus 4k, and we're multiplying that by 3 times the 3i, so that's 9i, 3 times the minus 2j, so that's minus 6j, and 3 times the 1k is plus 3k. So we're now going to solve the vector product of 2r multiplied by the 3q, that's the square bracketed term back here, we're just looking at that term only. So that's 2i minus 4k multiplied by the 9i minus the 6j plus the 3k. We can put that into determinant form here, there's the generic form we saw on a previous slide. In this particular case, the vector a would be the 2r, so the coefficients of vector a would be 2 in the I, 0 in the j, and minus 4 in the k. And for vector 3q, in our case, we'll get 9 in the I, minus 6 in the j, and plus 3 in the k. Now we're ready to solve our vector product of 2r crossed with 3q. Example 2, part 2 continued. I've just repeated this line here for convenience from the previous slide. Now we'll look at our determinants for I. So I, coefficients will be 0, minus 4, minus 6, and 3. And we get that by covering up this column and reading to the right the coefficients. The minus j, don't forget the negative j there, the coefficients will be 2, minus 4, 9, and 3. And we get that by covering up the central column and reading either side coefficients. And finally we get the plus k determinant, which is 2, 0, 9, minus 6, and we get that by covering up the final column and reading the coefficient to the left. So find the determinant for I, it's 0 times 3, take away minus 6 times minus 4, do the arithmetic on that, you get minus 24. It's 2 times 3, take away the 9 times minus 4, that'll give you 42. And finally we've got the 2 times minus 6, take away the 9 times 0, gives you minus 12. So the vector 2r multiplied by 3q gives us minus 24i, minus 42j, don't forget this negative here, we must carry through, and then plus the minus 12k. Just tidying it up, that's minus 24i, minus 42j, minus 12k. So now we've got the cross product of 2r with 3q. Example 2, part 2 continued. From the previous slide we worked out the vector 2r crossed with 3q, which gave us this value here in unit triad format. Now what we're going to do is multiply that by the p vector here. So we've got p crossed with the 2r times the 3q. So my header row, ijk here, my second row relates to the p vector coefficients, and my third row relates to the 2r times 3q vector. So we're going to solve as we did in the previous part of the question. So for the plus I determinant, we've got I minus 2, minus 42 and minus 12 coefficients, and again we get that by covering up this column and looking at the coefficients to the right. the minus j coefficients are 4, minus 2, minus 24, minus 12. It's formed by covering up the middle column and looking left and right for the coefficients, and then finally to get the plus k coefficients, that's 4, 1, minus 24 and minus 42 by covering up this column and looking to the left. I'll leave you with the arithmetic to review for this particular part of example 2. Very similar process we've already carried out before. Just be careful you carry this negative through when you write your ijk vector here. So what you should end up with is minus 96i plus 96j minus 144k. And all we've done on the last line is simply factorised on minus 48, which is common to all the terms. Example 3, a practical application here. We're asked to determine the moment and the magnitude of the moment of a force of I plus 2j minus 3k newtons about point B, which has coordinates of 0, 1 and 1, x, y, z there, when the force acts through a point A having coordinates 1, 3, 4, x, y, z again. So we're going to assume the origin O in this case is 0, 0, 0 because we're not told anything otherwise. So vector OA in this case will be I plus 3j plus 4k. So vector OA will give us a point here from the origin. Vector OB will be j plus k, and given in the question, and the force vector F is given as I plus 2j minus 3k. So that's all information taken directly from the question. Now the moment vector M about point B of the force F, which has a position vector we've termed that R from B, is given by the expression the moment is equal to R times F, R cross F. So R is the vector from B to A, so R is BA. So we're going to have to find R because that's basically our displacement or our distance from point B to A, and the force vector is applied at A. Example 3. So what we need to calculate first of all is the vector B to A. We need that as our distance from B to point A where the force acts. So from vector algebra, looking at the diagram on the right here, OB plus BA, in other words starting at the O and going to the B and then adding the B to the A, is the same as going directly from O to A. We want to find BA, labelled R on the diagram, so rearranging the equation, BA is equal to vector OA take away vector OB. So from the previous slide, vector OA was I plus 3j 4k, and we're taking away from that vector OB, which is 0 in the I plus 1 in the j plus 1 in the k. Doing the arithmetic on that, and I'll let you look at the change in sign here, we end up with vector R, or BA, is equal to I plus 2j plus 3k. So now we've got our distance between B, the point about which we're taking the moments, and point A, the location of where the force is actually applied, so we can find the vector product M, which is going to be R times F. So R in this case is I plus 2j plus 3k from the line above, and we're multiplying this by the force vector, which is I plus 2j minus 3k. This diagram on the right hand side is showing us the force applied at point A, and it generates a moment about B. So our force vector is applied at point A, and we're taking moments about B in this case. We're going to use determinants now, as we did before, to find the vector product of R times F. Example 3 continued. I just repeated the 3×3 determinant for M here for convenience. So we're now going to solve this. So the I determinant, we end up with coefficients of 2, 3, 2 and minus 3, and we get that by covering up the I column and looking to the right for the coefficients. For the negative j determinant, we end up with coefficients of 1, 3, 1 and minus 3. We get that by covering up the j column and looking to the left and the right of that column. And then to get the positive k determinants. That's 1, 2, 1, 2, and we're getting that because we're covering up the k column here and looking to the left. So we're going to evaluate then the I determinant, so that will be 2 times minus 3, take away 2 times 3, I'll give you minus 12. The minus j determinant is 1 times minus 3, take away 1 times 3, minus 6, and the k determinant is 1 times 2, take away 1 times 2. That will give you 0 in this case. So our moment, which is r times f, is equal to minus 12i minus the minus 6j, or if you like, that's minus 12i plus 6j, and that's in Newton meters. Example 3 continued. We're also asked to find the magnitude of moment m, and we do this by using Pythagoras' theorem. So the magnitude of m will simply be the minus 12 squared plus the 6 squared all square rooted. So 13.42 Newton meters the magnitude. Just some reference points here. In this example, we've calculated m by multiplying vector r by vector f, where r is equal to the BA. So we're taking moments about point B, and that gave us this vector. If you plotted it, that's what it would give you. And don't forget that relates to a moment that's going to be in a clockwise direction. Had we have calculated the moment is f times r is AB, then the change of sense would occur. The moment would be going in the opposite direction, it would be going in an anti-clockwise direction. So whether you have the r times f or the f times r, you will still get the same magnitude, but with vector products we know that there's a change in direction, and it's a change in sense of moment in this case. So just be aware of that. Exercise 2, we've got a force F of 4I minus 2J plus 2K newtons acts on a line through a point X that's given the coordinates of 0, 6 and 2, X, Y, Z. We've got to determine the moment vector M and its magnitude about point Y, which has the coordinates of 8, 0, minus 2, X, Y, Z, millimeters. I would encourage you to stop the presentation here and attempt exercise 2 based on the work we did on the previous slides. The answers are shown here in the square brackets and the solutions are given over the page, but I would encourage you to attempt it first before reviewing the solutions. Exercise 2. So we've got a force F of 4I minus 2J plus 2K newtons. It acts on a line through a point X, which has the coordinates of 0, 6 and 2. We're asked to find the vector M and its magnitude about a point Y with the coordinates of 8, 0 and minus 2. It's in millimeters. So we'll let O be the origin, and again the origin will be at 0, 0, 0, the centre of our coordinate system. Vector OX given in the question is 0I plus 6J plus 2K. So that's 6J plus 2K. And vector OY is given as 8I plus 0J minus 2K, so 8I minus 2K. And the force vector is given as 4I minus 2J plus 2K. That's the information extracted from the question. The diagram here I've tried to show the points plotted. This is point X, so we have O to X, and this is point Y, so we have O to Y. Now the force is applied at point X, and we've got to take moments about point Y. So what we need to do is work out the length of the YX vector, because that's the distance or the displacement we need to calculate. Exercise 2 continued. So don't forget we're calculating moment M about point Y. Point Y is defined here. Due to a vector F, force vector F, applied at X. So X is up here. So we need to calculate a distance YX, which has also been termed R in this particular diagram. So the moment of the force about Y will be R times F. So for vector algebra, we know that OX plus XY, so in other words from here to here, so X, and then X to Y, is the same as O to Y, same as the distance OY here. If we rearrange the equation, then XY is equal to OY take away OX. So OY, given in the question, is 8I plus 0J minus 2K, and we take away from that the OX, again in the question, 0I plus 6J plus 2K. Be careful with the negative here because that affects the signs of all the terms in the bracket. So we end up with take away the 0I, 0, take away the 6J, take away the 2K. So R, vector R, which is the Y to X vector, is 8I minus 6J minus 4K. Exercise 2 continued. So our moment is equal to the R times the F. This is the value of R in terms of unit triad from the previous page, and the force vector F is given in the question. It's 4I minus 2J plus 2K. Again, writing that in determinant form, we will end up with the moment R times by F is equal to the IJK in the first row. Second row we'll end up with minus 8, 6 and 4, which will be the coefficients for the R expression, which is up here. And then the third row we've got 4, minus 2 and 2, and that's the coefficient for the force vector F, which is this one here. Exercise 2 continued, just repeated vector M for convenience here with the coefficients for I, J and K. We're now going to solve for the determinants of I minus J and K, same way as we've solved on the previous examples. So for the plus I, the coefficients will be 6, 4, minus 2 and 2, and we get that by covering up the I column and looking to the coefficients to the right of that. Solve for minus J, we get coefficients of minus 8, 4, 4 in 2, and we find that by covering up the J column and looking to the left and the right for the coefficients. And to find the plus K determinant, it's going to be minus 8, 6, 4 and minus 2. We get that by covering up the right hand K column here and looking to the left for the coefficients. So now we can solve determinants I minus J and K. So I, don't forget, it's 6 times 2, the leading diagonal, take away, minus 2 times 4, the off diagonal, so 6 times 2 take away 4 times minus 2 here. Doing the arithmetic on that will give 20 for the I. I'll let you wander through the minus J and the K determinants. Don't forget to carry forward this negative to here when you bring all the terms together. What you should end up with ultimately is a moment M is equal to 20I plus 32J minus 8K in Newton millimeters. So that's the moment of the force about point Y. Exercise 2 continued, just repeated the moment M in its unit triad format for convenience. We're now asked to find the magnitude of vector M, so we'll use Pythagoras theorem here. So from above that will be 20 squared plus 32 squared plus the 8 squared, ignoring the negative of course there, all square rooted gives a value of 38.57 Newton millimeters. That's the magnitude of M. Example 4, another practical application here. The axis of a circular cylinder coincides with the z-axis and rotates with an angular velocity, symbol omega, of 2I minus 5J plus 7K radians per second. We're asked to determine the tangential velocity, v, at point P on the cylinder, whose coordinates is J plus 3K meters. We're also asked to calculate the magnitude of the tangential velocity. Now note from our mechanics work that linear velocity v is equal to the angular velocity omega times by the radius. That gives us a value in meters per second. So what we're going to do is work out v given the omega and given the r in this case. So the origin we'll assume to be 0, 0, 0 because we're not told otherwise, so that's the origin of the cylinder. The angular velocity omega from the question was 2I minus 5J plus 7K, and the radius of the point we're considering is r, which is J plus 3K. So velocity v at point P on the rotating body is given by v is equal to omega times r. In this case, the vector v is going to be 2i minus 5j plus 7k the omega multiplied by j plus 3k. That's a vector product, so we'll use determinants to solve this. So the omega times r, omega cross r here, given us a ijk in our first row, and then this is vector omega 2, minus 5 and 7, and this is vector r, 0, 1 and 3. So we're going to solve that using determinants. Example 4 continued, just repeated the omega r vectors for convenience. So we're going to solve our 3 by 3 determinant. First we're going to find the I determinant, so that's going to be minus 5, 7, 1 and 3 for the coefficients, and we get that as usual by covering up this column and looking to the right for the coefficients. The minus j determinant is 2, 7, 0 and 3, and we get that by covering up the column and looking to the left and the right of that column. And then to find the plus k determinant, that's 2, minus 5, 0 and 1, and we find that by covering up the k column and looking to the left for the coefficients. So the I determinant is minus 5 times 3, take away 1 times 7, arithmetic is shown here, gives a value of minus 22. I'll let you calculate the minus j determinant and the plus k determinant. They're given here for your reference. The minus j is 6 and the plus k is 2. Don't forget, as always, make sure you bring the negative down here from the minus j when you're doing your evaluations for omega r in this case. What you should end up with is v, which equals omega r, is 22i minus 6j plus 2k meters per second. That's the velocity in terms of the unit triad. If you want to find the magnitude of the velocity, again we use Pythagoras theorem. So applying Pythagoras theorem to the above vector is 22 squared plus the minus 6 squared plus the 2 squared, all square rooted, gives us a value of 22.89 meters per second. I'll leave you with some tutorial questions and encourage you to attempt as many as you can. Question 1 simply gives us two vectors, p and q, and wants us to find the vector product pq and the vector product qp. The answers are given over here in the brackets on the right hand side. You see the only difference between them is the change in sign between the vectors. Question 2 is given us three vectors this time. It wants us to find the modulus of vector p crossed with r, and it wants to find the modulus of vector r crossed with q. Question 3, again given us three vectors. This time it wants us to find 2 times the vector p and then cross that with 3 times the vector r. And part B of question 3 wants us to add vectors p and r together and then cross them with q. All the answers are given on the right hand side in the brackets. Question 4 and question 5 given here, similar kind of questions as on the previous slide. Part E of question 5 does want us to find the angle between the vectors, so you have to use the equation we derived previously for the sine of the angle equals to the a cross b over the modulus of a times the modulus of b. In question 6, similar kind of question, given vectors a and b. Going to find the angle again between the vectors. Question 7 is a descriptive question relating to forces applied some distance away from a point. We've got to calculate the total moment generated by the three forces and the distances. So you're given force 1 and distance 1, force 2, distance 2, force 3, distance 3. Essentially it wants you to work out three vector products here of F1R1, add that to F2R2, add that to F3R3. You should find the magnitude of the moment. Once you find the magnitude is 10 Newton meters. Question 8 is a force times distance question. It's very similar to the type of problems we've solved in our examples and exercises. Question 9 and question 10 relate to angular velocity type problems, and again we solved something similar in the example we shown on the previous slide. Again the answers are given in the square brackets against each question. And question 11 and question 12 stated here. Be careful with question 12 in the way it's worded. A force of magnitude 3 units acts at a point with coordinates 1, 2, 3, x, y, z. The force is applied in the direction of the vector 3i minus j plus 4k. We first of all got to determine the moment of the force about point O, and also we've got to state what the moment of the force would be about the point with coordinates 1, 2, 3. So because you've got a force magnitude of 3 units applied here, take the force vector, the 3i minus j plus 4k, and factor that by 3 to begin with, and then that accounts for the force magnitude of 3 units, and then continue the question in a similar vein as we have on the previous examples. Just be careful with the very last part of the question when it says what is the moment of the force about the point 1, 2, 3. That's the point where the force is applied. So think through carefully how you would answer that question. Answers are given here in the brackets. Here's a bibliography used to help generate the presentation. Some very good books again I would encourage you to review for further reading. I hope it's been of interest to you, and thank you for viewing.